right in and prove the Lagrange remainder theorem, which is usually called Taylor's remainder theorem, or Taylor's theorem.
Come on.
There we go. Okay. And what I claimed yesterday is that the size of Rn is less than or equal to the max over t of the n plus 1th derivative at t over n plus 1 factorial times x minus c to the n plus 1. That's what I claimed yesterday. What I want to do today is to prove this, and I'm actually going to make a slightly stronger claim. Hi there, would you close the door, please? We're going to actually refine this just a little bit. And I'm going to claim that, in fact, there is a t, let's call it t star, such that the remainder at x is exactly equal to the n plus 1th derivative at t star over n plus 1 factorial times x minus c to the n plus 1 for some t star between c and x, or x and c if x is less than c. Okay? So this is my claim. And the proof is awesome. It is a grand and glorious exercise in using Raleigh's theorem. And hopefully it will give you some insight into the nature of the remainders. So let's see if I can do this without running over my time. That's called math teacher start, in case you didn't catch that. Okay, what I'm going to do is we're going to start with an f of x, and we're going to start with its nth degree Taylor polynomial centered at some c right here. And this will be Tn of x right here. And actually, for clarity, I'm going to label this as actually f of t and Tn and Tn of t, because x is going to be a particular point of evaluation of our function, and the true value of f of x is sitting right here, and the estimated value, Tn of x, is sitting right here, and the actual retail remainder that we're talking about is this value, this difference right here. Rn is equal to f minus t. Just like that. And what I want to do is to find an expression for Rn of x. Sadly, as we've noted before, there isn't really a good analytic way to find an exact value for this. If there were, I could evaluate f and we'd be done.
If there were, we'd use it.
But what I'm going to do is I'm going to construct a function of t that's going to have a domain between c and x, and my function of t is going to be equal to the remainder plus an error correction term.
Teachers, pardon the interruption. The internet, the server is down in the building. We're working on getting that fixed. The phone lines are not acting correctly, and if you would like to send...
Okay.
T-cards are working this morning.
I stood outside for 5 minutes and the cold was going to let me in.
I couldn't ridiculous.
Okay. So we're going to construct this function, which is equal to the remainder plus an error correction term, and that's done a little bit sloppily. Let me write that again. It's going to be a constant times t minus c to the n plus 1. Now, the reason that I'm taking this particular form is not going to be apparent until we get to the end of the proof. However, I think you'll grant to me that I can construct a function any old way that I want, right? And now I'm going to put one further stipulation on it, I'm going to say that we're going to choose k such that h at x is exactly 0. We're going to choose k so that h of x right here at this point is exactly equal to 0. And that's not hard to do. All we have to do is let k equal f minus t all over x minus c to the n plus 1. In other words, we reverse engineer k. And so what we're looking for is a special form or some mathematical relationship about k that will be interesting to us. But before we do that, I want to take a look at what the graph of h of t might happen to look like. And h of t is going to be very interesting because what it does is to find the remainder, and then it adds on this error correction term. And it should be clear to you that the error correction term is exactly 0 when t is equal to c. And also, h of c is going to be equal to 0 as well because our Taylor polynomial has the property that it exactly equals the function at c. And not only that, but its derivative exactly equals the function's derivative at c. And not only that, but its derivative, its nth derivative, all of the k derivatives up through the nth are equal to all of the k derivatives up through the nth at x equals c. But sadly, when I take the n plus 1th derivative of my Taylor polynomial at any value of x, I get 0, because it is an n-degree polynomial. And so if I take n plus 1 derivatives, I get down to a constant, and then take the derivative one more time, 0. So this is the way that we constructed our Taylor polynomial to begin with. That means that when I look at h of c, specifically at the value c right here, h of c is going to be the difference between f and t plus this error correction term, which is 0 right here. And that means that h of c is going to hit 0, and it's also going to be really flat there. So that my h of c is going to look something like this. And then it's going to hit 0 again because we chose the k so that h of k is equal to 0. That's what my h looks like. Is everybody with me so far? This is the setup. Now that we've got the setup, the rest is really fun. I've already observed that h of c is equal to 0 because it's equal to f of c minus t n of c plus k times c minus c to the n plus 1, which is equal to 0 plus 0 or 0. Right. And I also have observed that h of x is equal to 0 because we chose k to make that happen. Well, we have a function, h, that has two values that are equal to each other, h of c equals h of x, and h is differentiable on the interval c to x, and therefore it is also continuous on the interval c to x. So therefore, there must exist a t, let's call it t1, so that h prime of t1 is equal to 0. That's Raleigh's theorem. And in fact, I can go back to the graph and I can find that value of t1. That value of t1 is right here where h has a horizontal tangent. Ta-da. But wait, there's more. Because h prime of t1 is equal to 0, let's examine h prime of t a little bit. H prime of t, according to the way that we've constructed it, should be equal to, help me out, r prime of t,
minus tn.
yep, plus the last term is like so. K is a constant.
K and
K
Times t
K.
minus c to the n.
Times,
Yeah.
T minus c to the n.
but we missed this
Coefficient.
N plus one.
times n plus 1.
Yeah.
Yep. Exactly so. Great. So this is h prime of t, and we have h prime of t1 is equal to 0, and we also have h prime of c is equal to f prime of c minus tn prime of c plus k times n plus 1 times c minus c to the n. Now, f prime of c is equal to tn prime of c because that's what it means to be a Taylor polynomial. So that we have 0 plus, 0 equals 0.
Where is this getting?
In other words, we have two places, T1 and C, where h prime of T1 is equal to, where h prime is equal to 0. Which means, using Raleigh's theorem again, that there has to be a T2 somewhere between C and T1, such that h prime prime of T2 is equal to 0. Using Raleigh's theorem for a second time, and remembering that the second derivative is the derivative of the first derivative. Going back to our graph, we can see where T2 is. It's right at the inflection point of our graph. That's T2. Okay? Well, let's do one more iteration of this so we can see the pattern. H prime of T2 is equal to 0. What is H double prime of T2 is equal to 0? What is H double prime of T? It should be F double prime of T minus Tn double prime of T plus, now let's do some special care and feeding on this one, K times n plus 1 times n times
C to the n minus 1.
to the n minus 1. That's exactly it. Okay? And so when I evaluate h double prime at C, I get f double prime of C minus tn double prime of C plus k times a little bit ugly.
Writing 0 this time.
Yeah, exactly.
This is ridiculous.
It is kind of ridiculous, but it's also kind of fun because this is exactly 0 because Tn is a Taylor polynomial. And this is exactly 0 because C minus C is 0. So we have h double prime of C is equal to 0 and h double prime of T2 is equal to 0. Guess what?
You can use it.
And if I use Raleigh's theorem again, how would it go?
There is a triple
There.
prime
There is a T3
in between T2
such that
E equals
H
0.
prime equals.
He,
is equal to 0.
I don't know
And-
what goes past inflection point, but it's gotta be something.
Yeah, it's actually hard to identify this on the graph. I'm not really sure. We're just going to mark it as T3. But the key is that we're getting closer to C as we do this, right? We're getting kind of squeezed in towards C. So that if my function continues to have n derivatives all the way out, you can see this is another way of seeing that ultimately we're going to land at C as a limit point for this process. And we can see therefore that eventually our remainder, as we get towards C, will head towards 0, which is kind of cool. But before we get there, we have to deal with our Taylor polynomial. I'm going to do a ... because this process will continue as long as T has any derivatives left to squeeze, non-zero derivatives left to squeeze out of it. So that ultimately we arrive at there is a Tn somewhere between T, C, and Tn minus 1, such that the nth derivative at Tn is equal to 0. Does everybody agree this process should be able to continue? All right. Well, let's carefully examine what the nth derivative of h is following the pattern. The nth derivative of h should be
The
nth derivative of f.
Minus the nth derivative of t.
Yeah.
And
So that was the easy part. Now, let's carefully match the pattern for the last term.
x minus c to f.
Yeah, we're going to have t minus c to the what power, though?
N minus.
Now we've taken n derivatives. When I took one derivative, I landed at n. When I took two derivatives, I landed at n minus 1.
Oh, so you,
So if I take n derivatives, then I land at what power of t minus c?
And minus
And
n
then-
plus 1.
Yes, in other words, 1.
I don't like that.
No, yeah, actually you like this because this is going to give us what we want. To the 1, okay?
okay.
And
N to the N minus 1.
what about our coefficient here? When I took one derivative, I had n plus 1. When I take two derivatives, I have n plus 1 times n. When I take three derivatives, n plus 1 times n minus 1. How many factors do I have?
N
Go then.
plus 1. No.
I have
And factors.
n factors. Yeah, I have k factors for k derivatives, right? And the highest one is n plus 1, and the smallest one is going to be n minus k plus 2.
Okay.
When I take when I take one derivative, it's n plus 1. So that's n minus 1 plus 2. When I take two derivatives, it's n, so that's n minus 2 plus 2. When I take three derivatives, it's n minus 1, n minus 3 plus 2. When I take n derivatives, it should be n minus n plus 2. So my last factor is 2. So that's n times n plus 1 times n minus 1 all the way down to 2. That's just n plus 1 factorial. The missing factor of 1 is invisible. And there we go. This is my nth derivative. Okay. And now I examine this at Tn. I've already got a place where the derivative is equal to 0. I better examine it at C also. And when I examine at C, I get the nth derivative at C minus the nth derivative at C plus k times 0. Well, because this is a Taylor polynomial, Tn of C is equal to Fn of C, and I get one last iteration to squeeze out of this, so that there is a Tn plus 1 somewhere between C and Tn, such that Hn plus 1, Tn plus 1 is equal to 0. And here's where the fun ride stops, because the n plus 1th derivative of t is equal to the n plus 1th derivative minus nothing, because my Taylor polynomial is an nth degree polynomial. Its nth plus 1 derivative vanishes.
I thought we just proved that those things equal 0.
What's that?
But wouldn't you go back to the top? We talked about how.
You're talking about here.
N plus 1 is just 0.
Not fn plus 1. F is a function.
But you said that t of n plus 1 was 0, and that equals
Yes.
f of n plus 1, so aren't they both 0? Like your little left-hand column at the top. That was in blue.
Here.
What we looked at here.
Yep. So we have my first n derivatives match the function. Once I get to the n plus 1th derivative, it stops agreeing with the function. And that's why my graph of Tn does not exactly line up with my graph of f. Its first n derivatives agree with the function, and then we get disagreement after you take the n plus 1th derivative and on down. Does that make sense? Yep.
And determine
And that's
how,
why we do this proof, by the way.
determine how many derivatives it takes to make it not agreeable. It just depends on the number of terms you have in your Taylor polynomial.
That's it. That's exactly right. The first n terms will match at C. Right. Now, what about my last term? My last term is actually pretty easy also. My last term is k times n plus 1 factorial times 1. And we have finally arrived at a point where this guy
Actually has down here in 0? This is
Yep.
not 0.
We found a place where h, the n plus 1th derivative of h is equal to 0, and therefore it must be the case that this guy right here is equal to 0 also. And this lets us solve for k, finally. K is equal to negative that, just like so. Well, okay, so what do I do with that? What I do with that is I go back to my original h of t, which was equal to f of t minus Tn of t, plus, and now I'm going to substitute the k value that I found. And if it's okay with you, I'm going to call the Tn plus 1 by a new name, just going to call it T star, times T minus C to the n plus 1. And the stipulation I had on h was this, that h of x was equal to 0. But now keep in mind that f minus t is the remainder. So this is Rn of x and what I require is that the Rn of x, the h of x is equal to 0 exactly when t is equal to x. And therefore, if I solve for Rn, I get the required form, which is that there is some t between x and c, so that the Rn is exactly equal to this, as advertised. What a crazy proof. But the cool thing about the proof is that it shows that my Taylor polynomial cannot be arbitrarily far away from the function. It is tied to the difference between the function and the Taylor polynomial is tied to the n plus 1th derivative of the function. Now, why do we do the max thing? Well, here's the problem. I don't know where t star is. I know it's between c and x somewhere, but I don't know what value it is exactly. So if I want to be safe, and this comes back to your arbitrariness question that you raised yesterday.
Yeah, I was about to mention that.
If I want to be safe, then what I have to do is I have to say that r can be no worse than the maximum possible value for all t's between x and c. And therefore, I have this expression. Certainly, Rn of x is less than or equal to the maximum possible over t's between x and c of the n plus 1th derivative of t over n plus 1 factorial times x minus c to the n plus 1, like that. And we just put the absolute values here so that my inequality makes sense in case we have a negative value here. And that explains why we did our substituting yesterday, like we substituted 3 for e and so on and so forth. It's not that e is actually equal to 3, it's that this guy right here could conceivably be computable. Whereas finding the particular value of t right here, unless you're extraordinarily lucky, is generally not going to be computable. So this expression is exact, but it's only theoretical. Because in general, I can't find this value of t, whereas this expression right here is inexact, but it is computable.
The next big thing in math is going to be finding a way to compute that.
Yes, although there are various reasons that mathematicians would sort of give up on that project.
Just like imagine someone being like math teacher told you, like, I remember when I was taught this, we couldn't find these, but now we have this nifty little theorem, and you just do
Yeah,
this.
this.
Yeah, well, so you got this
Someone
really interesting
stayed
thing.
up.
I think the answer to your question is we would make it computable to a certain number of digits by means of series. Think about sines and cosines. When I ask you what's the sine of 20 degrees, you reach for the plastic brain. Okay. But how is the plastic brain actually doing that? Well, it's doing it with a combination of lookup tables and series to actually generate a certain number of decimal points. And you look at 12 decimal points, and you're impressed enough that you say, oh, that's an exact value. No, it's not. It's an approximation to 12 decimal places. So, is that computable? It's computable enough. But the general answer is, yes, we can make this sort of semi-computable by using series to compute enough decimal places to make it happen. And this is the theory that undergirds it. I can not only compute a value, but I can tell you how good that value is. I can tell you how many of those decimal places are real, how many are just fake. And that's good enough for mathematics, at least at this time. Okay, so where does all this leave us? Well, it leaves us with some insight into the nature of the Lagrange error bound. The Lagrange error bound is putting a bound on how far away my function can be from the Taylor polynomial. And the answer is, the further away that I get from C, the further away f can get from its Taylor polynomial representation. Now, I wonder if we have enough time to look at 15. If not, I'll do something third period for the video. So we're looking at page, I think it's 500.
Yes.
And number 15, we're looking at the function x e to the x. And they ask you first to find the Lagrange series, and then establish that that it converges for all x. First of all, I hope all of you have discovered that finding the Lagrange series for these functions is best done with manipulation of known series rather than derivatives, right? So if I start with g of x equals e to the x, which is 1 plus x squared over 2 factorial, and I establish an nth term for this guy, then f of x, which is x e to the x, is simply x times all of that, which gives me x plus x squared plus x cubed over 2 factorial plus, what's my nth term?
X to the m plus 1 over n factorial.
Yeah, that's it. Just n factorial. We'll do this and then I'll turn you loose because it's fairly straightforward. So there's my Maclaurin series for this guy. Now I want to establish convergence, and so I'm going to take the limit as n goes to infinity of Rn of x, which is equal to max over t of, let's see here, the n plus 1th derivative.
Yeah, that was my problem. It was like, how do you,
at t over n plus 1 factorial times x minus c to the n plus 1. Okay, so we need a pattern for this guy, and actually I don't think we'll be able to establish that pattern in just 1 minute. So I'm going to turn you loose, and we're going to leave this as we've got to find a pattern for the n plus 1 derivative.